Hello, I'm about to do or attempt to do question 5 of this year, that is 2025's International Mathematical Olympiad. And as I briefly mentioned on the previous video where I did question 4, this one has a particular interest for me because I know the person who set it, and if I get permission from him to mention his name, which I expect I probably will, then I'll put something in the description of the video, but below. Anyway, so let me just do the first of all. I'll share my screen and I'll look at the problem and write it down. So uh, here we go. Right. So what is the problem? Okay, it's I think I may need to write down quite a lot here. So Alice and Bazza. So you can tell this person's not a computer scientist because then it would be Alice and Bob are playing. That's just a little in joke in case you are a computer scientist. Are playing the in equality game. So perhaps the main problem is where does this name come from? But well, maybe we'll see. Maybe it'll become clear as I read more of the problem. A two-player game, I won't write everything down, whose rules depend on a positive real number lambda. So depending on some real number lambda known to both players. I cannot guess where this is going. On the nth turn, the following happens. Okay, so on the nth turn, and it mentions start at n equals 1. The following happens. I won't write those words. So if n is odd, then Alice chooses a non-negative real number, and the property it must have is that x1 plus x2 up to xn is less than or equal to lambda n. So far, so good. And if n is even, presumably, yes, if n is even, Bazza chooses a non-negative real number. And what's the condition that Bazza must satisfy? Such that the sum of the squares is less than or equal to n. That is quite interesting. If a player can't do a valid move, then obviously the other player wins. If it goes on forever, it's a draw. If it goes on forever, well, it just says here neither player wins, but whatever, I'll just say then it's a draw. All chosen numbers are known to both players. I think I won't bother to write that down, just to take that as read. And then a not totally unexpected question, for which lambda does Alice win? And for which lambda does Bazza win? I'll scroll back down again in a minute when I've got written that lambda does as a wind. But in keeping with my previous practice, I'm now going to remove the page that's got the problem statement, although in fact, again, it's another, as with problem 4, it has a video solution. So I wouldn't have noticed the solution by mistake. So let's get that back, get the whole question back. And so I have a common feeling when faced with an Olympiad problem like this of not having the faintest idea where to start when I look at it, or have that sort of sensation. Of course, I've got all sorts of standard problem-solving techniques up my sleeve. For example, one that I could try is just picking some value of lambda and seeing what happens. And I think I may end up doing that. But for the moment, I just don't have any particular feel for how this is going to work and who's going to have a winning strategy. For example, one fairly natural conjecture might be that if lambda, the larger lambda gets, the better it is for one of the two players. And if that's the case, I don't even know whether it would be Alice who wants it to be big or Bazza who wants it to be big. Why would it be called, now I've written the whole thing down, inequality game. I feel a bit stupid like that. Because if I read inequality as inequality, I see it becomes inequality. Okay, so I was a bit slow there. Inequality, perhaps it's because I'm British English and not American English or something like that. Right. So what would be a first subsidiary question? If I can't answer the main question yet, what would be a question that I could ask? So question 1. Is there a value of lambda such that Alice wins? The value of a question like that is not that it's a particularly interesting question. The answer must surely be yes. So it would be a rather strange problem if the answer were that Alice couldn't win. But the idea would be that one would get an example of lambda such that Alice wins, and then attempt to, the sort of reason for asking this is you answer this, and then you try and generalize the answer and get as much juice out of the answer as you can. But I don't, as I said, I still don't really have any feel for how to do it. Actually, perhaps I could also ask question 2. Is there a value of lambda such that Bazza wins? It's going to be difficult not to call Bazza Bob from time to time, but I nearly did just then. I'm asking that one actually. I suddenly thought I'd ask that as well because I see that there's a I want to just check that it was meant to be less than or equal to no, I won't. Well, I will check because it'd be tragic if I'd got the question wrong. I think it is, but so please excuse a small delay because for some reason this website with the problems on takes a very long time to load. Just while I'm waiting for it, I suppose I'll just say I think it's loaded. Yes, I have got the question right. All right, so I think at least one of these questions has an easy answer. So I think if lambda is big, then Alice can choose x1 to be reasonably big, and then Bob has done it. Okay. And then Bazza has no chance of choosing x2 because x1 squared will already be greater than n. So let's say if lambda is greater than 1, then Alice can choose x1 equals lambda, after which well, and then x1 squared is, so x1 equals lambda certainly satisfies the condition that x1 is less than or equal to lambda, and then x1 squared is equal to lambda squared is greater than 1, so x1 squared plus x2 squared, I'm spelling it out, is greater than 1 implies whatever x2 squared is implies let's just say Alice wins. So indeed the answer to question 1 was a rather easy yes. Of course I will now be interested in whether there are other values of lambda such that Alice wins, in other words values that are not greater than 1. In fact, let's just consider, I think it seems rather natural since I got lambda greater than 1. So to say to think about what happens when lambda equals 1. So what happens, well, let's say who wins, if anyone. So I'll go back to what happens because it could be a draw. What happens if lambda equals 1? So it's not even obvious what the right strategy is, but I would guess that so I'll consider what happens if Alice chooses x1 to be 1. So Alice chooses x1 to be 1. That forces, so then x squared equals 1. That forces Bazza to choose x2 to be 0. And now Alice can choose x3 to be 2. And if Alice chooses x3 to be 2, then x1 squared plus x3 squared is 5, which is already bigger than 4, and so Bazza loses. So I'll just write it like this. This means Alice chooses 1, and by implies, I mean that it's forced if Bazza doesn't want to lose straight away. Wait a minute, why did I say that? Scratch that. So I haven't yet. Oh, I think I may have got the, I think I may have accidentally, sorry, x1 squared plus x2 squared should be greater than 2, so something went a bit wrong there. So let's scratch all this. I got it wrong. I was, I don't know, half asleep. I get rid of all this for the moment. So I want to go back to the question, and in fact, even this I have to get rid of. I just want to find a single value of lambda such that Alice wins the game, if I can. And I suppose it is still reasonably easy because I mean, it's easy to find a single value. If lambda is really big, we'll see how big it needs to be for this argument to work. But let's suppose if Alice chooses x1 equals lambda, then x1 squared plus x2 squared is greater than or equal to, whatever Bazza chooses, is greater than or equal to lambda squared. So if lambda is greater than root 2, that's what I should have said before, then Alice wins. Right, I'm off from a slightly better footing. So the answer is still yes, but the range of lambdas I've proved, for which I have proved that Alice has a winning strategy, is actually lambda greater than root 2. So the question that is sort of morally similar to the question I was asking before is then what if lambda equals root 2? And I think Alice will probably have a winning strategy here as well. So if Alice goes for root 2, then Bazza is forced because x1 squared plus x2 squared has to be less than or equal to 2, and x1 squared already equals 2, has to choose 0. Then what? So now we have that x1 plus x2 is root 2. So we need the condition that Alice must satisfy is going to be root 2 plus x3 is less than or equal to 3. So I'm just going to, so this next move is not forced. But what if Alice chooses 3 minus root 2? So I'm sort of interested actually. Another question that is occurring to me is, so I'm going to put it down here somewhere, is a greedy strategy. I'll explain what I mean by that in just a moment. Always best for Alice. In other words, does it always favor Alice to choose her number to be as big as possible, given the constraints? And certainly if Alice wants to defeat Bazza at the next move, then Alice should make life as hard as possible for Bazza by making her number as big as possible. But what if Alice can't defeat Bazza at the next move, but only the sort of somewhere down the line? Perhaps it's not completely obvious that it isn't better for Alice to sort of hold back a little bit. But perhaps it is obvious. Perhaps there's a proof that Alice should always make her number as big as possible. Maybe that'll become a little bit clearer if we can find a value of lambda for which Bazza wins, which so far we haven't done. So if we do this, then let's just, I've got to do some slightly irritating calculations, but what's the sum of the squares of these? We get 2 plus 3 minus root 2 squared, which is 9 minus 6 root 2 plus 2, which is 13 minus 6 root 2. And 6 root 2 is less than 6 times 1.5. 6 times 1.5 is 9. So this is greater than 4. So what I've just shown here is x1 squared, with these choices, x1 squared plus x2 squared plus x3 squared is greater than 4. So Alice wins. And was Alice a positive real number? No. But yes, because, or non-negative real number. Because in fact, well, Oh, I suppose you could say if lambda, uh, all right, maybe we should add the sort of trivial answer to question two, because I just said lambda was a real number, so I might as well go with that. So observation, I don't know quite how to say where to scale from, but if lambda is less than 0, then Bazza wins because Alice can't even move. Okay, so we could say, can Alice do a first move? And the answer is that's where that condition that lambda should be non-negative comes from. So so I want to modify question 2. So I'll make it a new question. Question 5, is there some lambda greater than or equal to 0 such that Bazza wins, because it was a bit boring. And as before, we might as well look at the boundary case. So what happens if lambda equals 0? And this I'm not going to write down because I've actually also, it's quite easy to do in one's head. If lambda equals 0, then x1 is going to have to be actually no, then Bazza wins easily. I thought that was going to be a draw, but I thought it was going to be everybody had to choose 0 all the time. But the Bazza's condition doesn't involve lambda. So actually, if lambda is 0, then Alice is forced to choose x1 to be 0, but then Bazza can choose x2 to be root 2 or 1 or any positive number, and then Alice is in deep trouble for x3. So actually, the answer to this is yes. Bazza can choose. So Bazza wins if lambda equals 0. And it was fairly obvious that that argument was going to work even for some lambdas bigger than 0. That would be the obvious next question. But perhaps since I can already see that the answer is going to would be the next natural question, is there some lambda greater than 0? But instead what I'm going to ask is, how large can lambda be if Bazza wins because, I don't know how to put this, because Alice can't choose x3. There we are. So let's just quickly answer that question. It's going to be an easy one to answer, I think. So although actually perhaps it's not totally straightforward, because we have to work out what Alice's best strategy is. So perhaps I'll say we know that, let's not even try to say exactly what Alice does. We just say, what do we know about x1? It is some number between 0 and lambda. Now, if Bazza wants to defeat Alice at the next move, then Bazza is going to will need to choose x2 to be as large as possible. So what is the largest that x2 can be? So it'll be 2 minus x1 squared square rooted. So x2 squared will be, because we know that it can't, yeah, that's the condition that x2 squared has to satisfy if Bazza wants to do a valid move. So that already tells us that lambda has to be less than or equal to √2, but let's just say then x3 there'll be, so here's what I want to say. No valid x3 if x1 plus x2 is already bigger than 3. So if x1 plus the square root of 2 minus x1 squared is greater than 3. But is that, sorry, is greater than 3 times lambda. And so now we want to ask ourselves, so what Alice will want to choose x1 to minimize x1 plus the square root of 2 minus x1 squared. That's annoying. Let's just get a feel for it, because it's annoying because working out where that's minimized seems a little bit tedious. But if x1 is 0, we get √2. If x1 is lambda, we get lambda plus the square root of 2 minus lambda squared. I'm just trying to work out whether I believe that this number, whether this function of x1, what its behavior is. I think it'll certainly start out increasing. We wanted to make it as small as possible. So we can get it to be √2 by choosing x1 to be 0. The question is, can we make it smaller than √2? If I choose x1 so that this is 0, I choose x1 to be √2, then this part becomes √2, so we get another √2. So it's believable that the graph of this is going to look something like that. And perhaps I should be able to, it's just some Triggs type thing that this looks like. A sort of sine plus a cos or something, but it'd be sort of √2 times a cos, but yes, if I just, I couldn't, if I substitute x1 equals √2 sine theta, then I get, in here, I get √2 sine theta plus square root of 2 minus 2 sine squared theta equals √2 times sine theta plus cos theta. And sine theta plus cos theta is sine theta, and here's cos theta. It sort of goes like that. And I could use addition formulae for sine and cos, but I think I won't bother with that detail. So this is minimized at the two extreme points. So actually, so Alice has two options here. One is to choose x1 to be 0, making it as small as possible, and the other would be to make x1 to be root 2. Which she may not be able to do. It will depend on what lambda is, but so in any case, this number here is at least root 2. So we must so if root 2 is greater than 3 lambda, then Bazza wins at n equals 3, by which I mean Bazza wins at the point where, because Alice can't choose x3. So let me just quickly check that I really believe that. So my argument will be Alice chooses x1, Bazza then chooses, Bazza has nothing to lose by choosing x2 to be as large as possible, and as large as possible means 2 minus x1 squared. And then Alice will be in trouble if x1 plus root of 2 minus x1 squared is greater than 3 lambda. And indeed, the smallest this can be is the square root of 2. So we get the condition that if root 2 is greater than 3 lambda, in other words, lambda is less than root 2 over 3. And I wanted to say a bit more. So I've just said that if lambda satisfies that condition, then Bazza wins at x3. If lambda doesn't satisfy that condition, so if lambda, let's say, is greater than or equal to root 2 over 3, then Alice could choose x1 equal to 0. Then Bazza would choose x2 to be root 2 minus x1 squared, which would be root 2. And then Alice would be absolutely free because 3 lambda is greater than or equal to root 2 to choose x3 equals 0. So that demonstrates that this was an if and only if. So the answer to that question is lambda less than root 2 over 3. Now, while working that out, I noticed that if Alice is trying to defend against Bazza, but unsuccessfully, sort of Alice's best bet seems to be to choose 0 every time. So, for example, actually, so if, for example, lambda actually equals root 2 over 3, in fact, I think that's going to be my next question, question 7. What if lambda equals root 2 over 3? And actually, there's a sort of interesting symmetry there. So if going back to when lambda was less than root 2 over 3, if Alice chooses x1 to be instead root 2, then Bazza has to choose x2 to be 0 because x1 squared plus x2 squared has to be less than or equal to 2. And so actually it makes no difference. So in other words, if Alice chooses 0, Bazza will choose root 2 and so x1 plus x2 will be root 2 and x1 squared plus x2 squared will be 2. And if Alice chooses root 2, Bazza will choose 0. And so again, we have the same sum and the same sum of squares. So there's a sort of funny symmetry there that Alice chooses the smallest possible but if lambda is less than root 2 over 3, Alice cannot choose root 2. So something was a little bit strange. So we seem to have we've got this natural barrier at root 2 over 3, also have a natural barrier at root 2. So far, what have we got? We've got that Alice wins. Let me quickly scroll back and just check. I think Alice won if lambda equals root 2. Actually, I could do a similar thing here and ask, because I had a bit of elbow room with this strict inequality here. For what values of lambda does Alice win at n equals 4? And that seems to be a line of approach that is going to be quite interesting to pursue. And whether, in fact, that there will be fairly simple, whether it will be possible to prove something like, if Bazza wins against such and such a strategy, then Bazza must win against all strategies, and then similarly for Alice. But let's quickly think about what happens if lambda equals root 2 over 3. So I think it's going to be the case that if Alice chooses something that's bigger than 0, then Bazza will choose, and then Bazza goes for this choosing as large as possible strategy. So we've got x1 plus root of 2 minus x1 squared. That's strictly bigger than root 2 now because of this little calculation here. Then that number will be bigger than root 2 or bigger than 3 lambda, and there'll be no valid x3. So therefore, Alice must choose naught. And let's say that so we don't know for sure that Bazza is going to be greedy, but if Bazza is greedy, if Bazza chooses root 2, then Alice must choose naught again because because 3 lambda is root 2 and we've already added up to root 2. So now let's think what happens if, so where have we got to with the sum of the squares? We've got 2. So the sum of the squares has got to be at most 4 after Bazza's next move. So if Bazza chooses root 2 yet again, then we have, what have we got to now? The sum of the numbers themselves is 2 root 2. So 2 root 2 plus Alice's next choice, x5, has to be less than or equal to 5 root 2 over 3. Which is looking problematic because 2 root 2 is 6 root 2 over 3. So that's already bigger than 5 root 2 over 3. So if we consider what happens at x at the fifth stage, then we see that Bazza not only wins, but wins with a bit of room to spare, because we had this is actually not just impossible, but impossible by quite some way, because this number here is strictly less than 2 root 2. So I now want to ask myself the following question, because it seemed that Bazza's best bet was simply to choose numbers as large as possible. So question 8, for which lambda does Bazza win with a greedy strategy? And by greedy strategy, I mean choose, I choose x. So Bazza's thing will always be even as big as possible. It looks as though that may involve some unpleasant calculations, because Alice might not choose. I mean, if Alice chooses 0 all the time and Bazza chooses as big as possible, then that's one thing. But if Alice, but why would Alice choose 0 all the time? And if Alice doesn't choose 0 all the time, does it get very unpleasant? But actually, because Alice choosing 0 all the time looks as though it might be sort of nice, I'm going to ask a simpler question than question 8. So that's question 8, but with Alice choosing 0 all the time. And the reason I'm asking this is that it feels as though it might actually be some sort of extremal situation that might lead to at least a conjectured answer for what to the whole problem. It might be that sort of whatever the answer to this question is turns out to be the answer to the whole question, but of course that would then take some proof. So let's just have a look at this in case it gives us some insight. So if Alice chooses 0 all the time, then we can actually say we can sort of say x1 is going to be 0, x2, we need the sum of the squares to be at most 2, x3 equals 0, and then x4 is going to be, so again, the sum of the squares has to be at most 4, so we'll go for root 2, and there's a pretty clear pattern emerging here. x5 equals 0, because we're hypothesizing that Alice always chooses 0, and then x6, in order to make the sum of the squares up to 6, we've already got 2 plus 2, so we need another 2, so we have a root 2, so that when we square it, we get that 2, etc. And sort of when will Alice, so Alice, for Alice to survive, she needs at the, so what happens at stage 2n plus 1? We have that the sum of all these numbers is root 2 times n. and that has to be less than or equal to lambda times 2n plus 1. I'm not quite sure, I want to check whether I got that correct. So for example, at the 5th stage, she needs 2 root 2 to be at most 5 lambda. Yes, I think that is correct. So we need, so that needs to be true for all n. So it's rewriting lambda is greater than or equal to root 2 times n over 2n plus 1. So if lambda is less than root 2 over 2, that's eventually going to be violated. So that's again for all n. So lambda must be greater than or equal to root 2 over 2. And I think we've actually that argument may also prove a certain interesting statement, which is that if Alice chooses 0 all the time, then that strategy will at worst lead to a draw if lambda is wait a minute. So question 8 was for which lambda does Bazza win? So that was for Alice to survive. So if lambda is less than root 2 over 2, then Bazza wins. If Alice plays that strategy, plays the 0 strategy. Now, because of that symmetry thing that I observed earlier, I'm wondering whether actually that's going to be whether that's actually going to prove that Bazza wins even if Alice plays some other strategy. Let's just quickly think about that. Well, I'm going to write down the things that I plan to think about next. So question 10 does, so still on the assumption, if, I think the answer to this is going to be yes, if lambda is less than root 2 over 2, does Bazza win? So regardless of the strategy of Alice. And question 11, if lambda is greater than or equal to root 2 over 2, is it true that Bazza can't win? Which I believe is the case because I think that the 0 strategy defeats Bazza in that case. So let me just quickly check question 11. If Alice plays 0 strategy, so in other words, I think this is an if and only if Alice plays a 0 strategy. So if Alice plays the 0 strategy, then we can't actually say that, we can say that if Bazza plays a greedy strategy, then x2 will have to be root 2, x4 will have to be root 2, and so on and so forth. But if we just know that Alice plays the zero strategy, then for every n, no, for every m, let's say, x2 squared plus x4 squared plus up to x2m squared is less than or equal to 2m. And I want now to apply a bit of Cauchy-Schwarz or something like that. So that implies that x2 plus x4 plus x2m is less than or equal to, how can I maximize, oh dear, this is something that I sort of do all the time, and yet so this thing here by Cauchy-Schwarz is less than or equal to root m times the root of x2 squared plus x2m squared equals, sorry, is less than or equal to root 2 times m. Because that one's less than or equal to 2m, that one's less than or equal to, the thing inside the square root is less than or equal to 2m. So this is less than or equal to root 2 times root m multiplied by another root m, we get root 2 times m, which equals, so if 2m equals n, this is root 2 over 2 times n. So and it's also, it's less than or equal to root 2 over 2 times n plus 1. So that means that if Alice then plays 0, everything's going to be okay. So the answer to that is yes. So I'm now zeroing in on I've got a pretty strong conjecture. I believe that the answer will be that if lambda is less than root 2 over 2, then Bazza will win. And I believe furthermore that Bazza will win by playing greedily. So let's make that a new question. This is a further elaboration of question 10, or specialization of question 10. If lambda less than root 2 over 2, does Bazza win with the greedy strategy? But I just feels as though, oh yeah, so I've asked something closely related to that, but now I've got an actual conjecture for the lambda for which Bazza wins with a greedy strategy. So let's try and analyze what happens with the greedy strategy. So Alice chooses x1, and then Bazza chooses square root of 2 minus x1 squared. So that now adds up to, the squares add up to, we've got x1 squared plus 2 minus x1 squared, we've got up to 2. Alice chooses remember Alice is no longer restricted to the zero strategy. So Alice chooses x3. Bazza will now choose the square root of 2 minus x3 squared. Maybe a small thing to be absolutely clear about is whether I can be sure that x3 will never be, that won't be bigger than root 2, because otherwise Bazza will not be able to choose root of 2 minus x3 squared. I'll come back to that question. So on the face of it, we've got something like this, but there's a little bit of something that I need to check here. x5 squared, and so on and so forth. All right. So then we have that x1 plus root of, bearing in mind that we know that x1 can't be as big as root 2 because lambda is meant to be something that's smaller than root 2 over 2. So x1 is definitely smaller than the square root of 2. And so therefore the inside of this thing is definitely not negative. So we're in okay shape here. So that number here, the sum of the first two things is going to be definitely greater than root 2 with equality only if x1 equals 0, because x1 can't be up to the square root of 2. And then we know that, so now we've got that that's greater than root 2, which is greater than twice, that's greater than twice root 2 over 2, or greater than 2 lambda. So this root 2 is 2 lambda, so that's bigger than 2 lambda. So this number here is going to have to be smaller than lambda. So again, it'll have to be smaller than root 2. And I think we're going to be able to keep repeating that argument. So this number, the sum of those two, x3 plus square root of 2 minus x3 squared, is then by the same argument greater than root 2. Oh, sorry, I should have said greater than or equal to root 2 and greater than or equal to root 2. But because these things are greater than or equal to root 2, the sum of those and those is at least 2 root 2 or 4 lambda. So x5 has to be less than or equal to lambda, and therefore less than root 2. So this argument just can keep going, which means that if Bazza plays the greedy strategy, then Alice cannot do better than the zero strategy. And so we have, we're into the situation, because if Alice played x1 to be greater than 0, this would be a strict inequality, and then it just means that Alice is trying to make the sum as small as possible in order not eventually to be forced to make it big. Bazza has absolutely no trouble keeping the sum of the squares to be exactly equal to 2. And so the answer is yes. Now, I need to take stock, so that's quite a lot of progress. We know that if lambda is greater than or equal to root 2 over 2, Bazza can't win. And if it's less than root 2 over 2, then Bazza does win. So the answer, so going back to what the actual question asked, we've sort of answered half the question. We've answered for which lambda does Bazza, oh, no question mark. So for which lambda does Bazza win? So we can say Bazza wins if and only if lambda um, is less than root 2 over 2. I believe that if Bazza plays the greedy strategy, when lambda equals root 2 over 2, it's a draw. Let me just check that. So I claim that Alice doesn't have a winning strategy. And my argument for that would be if ever, so let's suppose Bazza plays a greedy strategy, then if ever this number is bigger than, say if this number is bigger than root 2, that will have to be, how is this going to work? Actually, I'm not absolutely sure about this. So we know that Bazza can't win. Oh, yes. We've established that Bazza can't win if lambda equals root 2 over 2. If Bazza plays a greedy strategy, then Bazza also can't lose because Bazza can, the same argument that showed that Alice is always going to have to choose these xi's to be less than root 2 shows that when Bazza plays the greedy strategy, these two numbers, sorry, the squares of these two numbers add up to 2. And so if Bazza can always ensure that the squares of these two numbers add up to 2, Bazza doesn't lose. So the answer to that is yes, and that's actually rather interesting. So let's just say I have a new question for which lambda can Bazza avoid defeat by playing the greedy strategy. What I'm very much hoping, because let's go back to what we knew about Alice. We knew that Alice won. Actually, I think we're going to have to be a little bit more sophisticated in our analysis of when Alice wins, but because I think so far we've just analyzed what causes Alice to win after one or two moves, but we're going to need to look at something a bit more than that. But maybe we can answer this, and perhaps that will give us a conjecture for when Alice will take over, so to speak. So what we'd like is to say Alice chooses x1, and then Bazza chooses square root of 2 minus x1 squared. Alice chooses x3. Bazza chooses 2 minus x3 squared root of, and so on. But as we observed before, or noted before, this strategy is not necessarily possible. It depends on x1, x3, and so on, always being less than or equal to the square root of 2. So if somehow we know that Alice's moves are always going to be less than or equal to the square root of 2, then we know that Bazza can just play this strategy and will never get into any trouble because the numbers will add up to exactly n at every even move. There's some of the squares, I mean, will be n after every even move. So what are the constraints that Alice is going to face? So in order to defeat Bazza, Alice is going to want to try to be able to play an xi that's bigger than √2 at some point. So in order to be able to play an xi that's bigger than √2, the constraints that Alice faces are ones where all the numbers up to xi add up to at most lambda times I. So in order for xi to be as big as possible, she's going to want the sum of the earlier ones to be as small as possible. And what's the smallest that they can be? Well, we've already established that assuming that all the previous ones are less than √2. So here, I'm going to write something down here. So if Alice can play a number greater than √2 at some point, suppose the first point is 2r plus 1, or let's say that the first is x 2r plus 1. So the first moment at which Alice is in a position to play a number greater than √2 is x 2r plus 1. So then I want to say, if Alice replaces all earlier x2s plus 1s by 0, then that we're assuming that Bazza is playing the greedy strategy, so that will just reduce this sum to √2. Otherwise, it's bigger than √2. So that reduces x1 plus up to x2r on the assumption that Bazza is playing this greedy strategy. So allows x2r plus 1 to be bigger. So we may assume that Alice plays 0 strategy up to some point, and then a number bigger than square root of 2. So now we want to know for which lambda is that not going to be possible. So here's how the game goes. It goes 0 and then √2, 0, √2, 0, √2, and so on up to √2. And then at this point here, a number bigger than √2 is played by Alice, and that the sum of these numbers has to be still less than lambda times n. So let's say that is at the stage, that's xr plus 1. So the condition on xr plus 1 is that, so we've got are root twos. So root two are um, and plus um, root 2 is strictly smaller than lambda times, well, that should have been 2r plus 1, lambda times 2r plus 1. Check that I got that right. So root 2r plus x2r plus 1 has to be less than or equal to lambda times 2r plus 1. And so the if I am to be able to choose x2r plus 1 to be strictly greater than root 2, that tells us that root 2r plus root 2 is strictly less than lambda 2r plus 1. So then that will enable me to increase this root 2 up to some x2r plus 1 and get something that's greater than or equal. So this is just the condition, this is not the condition for Alice to win, but it's just a condition for Alice to be able to defeat the greedy strategy or make the greedy strategy no longer possible, but that's actually not necessarily going to be, that's interesting, that's not actually going to be a victory for Alice necessarily, because Bazza can always depart from the greedy strategy, but still, let's just see what that gives us. So we get root 2 times r plus 1 is less than lambda times 2r plus 1. So lambda has to be greater than root 2 r plus 1 over 2r plus 1, or some r. But the odd thing is that it seems to work early on, and we get but we're already assuming that it's greater than or equal to root 2 over 2. So it seems as though when lambda is bigger than root 2 over 2, then the greedy strategy, well, aha, said something slightly wrong here. So when Bazza plays the greedy strategy, it won't actually be, this won't be the number that Bazza will necessarily play. So but if Bazza can't play this number, that seems a little bit problematic for Bazza. If Bazza can't play that number, that tells us that x1 was bigger than root 2, and so I'm actually sort of starting to wonder whether Alice is going to win if lambda is strictly bigger than root 2 over 2. So I'm going to ask question 14. Does Alice win if lambda is bigger than root 2 over 2? And in fact, I have a sort of proposed strategy for Alice, which is what I've analyzed here. Does Alice win by playing 0 for a while, and then choosing an x2r plus 1 to be as large as possible. So Alice's strategy here is just to go 0, 0, 0, 0, and then at some point, Alice wants to pounce and say, I'm going to choose x2r plus 1 to be so big that actually the sum of the squares of all the numbers up to this x2r plus 1 is going to be too big for Bazza to be able to have a chance. I feel quite optimistic about this strategy, but let's just see what happens. How easy is this going to be to analyze? Again, I think I don't want to sort of start saying what happens if Bob uses this strategy, because then I get involved in lots of cases and so on. So I'm just going to do what in automatic theorem proving trade we will say we'll choose meta variables. So Alice is choosing 0 all the time, and Bazza is choosing some numbers, x2, x4. We don't know what they are, but we're going to be able to say a few things about them in a minute. So what conditions must Bazza's numbers satisfy in order to defeat this strategy? So, and also to not to be consistent with the rules of the game. So Bazza needs x2 squared less than or equal to 2, x2 squared plus x4 squared less than or equal to 4, and so on. Let's say, well, we'll go up to x2r. So we want to say, when will it be possible for Bazza to defeat this strategy at the sort of 2r plus 1 stage? So all the way up to x2 squared plus x4 squared plus all the way up to x2r squared. That has to be less than or equal to 2r. And what will Alice now choose? So Alice then will choose x2r plus 1. She's going to make it as big as it possibly can be. So that'll be lambda times 2r plus 1 minus x2 plus x4 plus x 2r. And what is the condition that and so we will Bazza is going to, it's going to be very important for Bazza that x2 squared plus x4 squared plus x2r squared plus this x2r plus 1 squared number here. I'll just write it as x2r plus 1 squared, but it should be understood that x2r plus 1 is this. That should definitely be less than or equal to 2r plus 1. Because if it's bigger than 2r plus 1, then Alice has played a valid move that has led to a sum that's bigger than the sum, I mean, led to a sum of squares that's bigger than what it's allowed to be. Wait a minute. Has to be less than or equal to 2r plus 2, I beg your pardon. So that then if Bazza plays 0, then he'll be okay. Now that looks a trifle complicated, but maybe I can. Yep, so I think Bazza has nothing to lose by making all these numbers equal to each other, because if you replace all of x2, x4 up to x2r by their average, that's not going to affect x2r plus 1, but it's only ever going to make this sum of squares smaller. But I'm going to write that down because that's a rather important point. So replacing all x2k by x2 plus x2r over r doesn't alter x2r plus 1. And the only thing I really need to be absolutely sure about is that I'm not going to have a problem with these inequalities here if I do that. But if I've replaced all these numbers by their average, I've made this sum of squares smaller, so it's still less than or equal to 2r, which means that each xi squared is less than or equal to 2, and therefore we do get all these inequalities. And it sort of preserves those inequalities which I've collected together with this star. So I still haven't decided what that average should be, but so let's make it, so suppose x2k just equals some particular number x for every k, then what are the conditions? So we need, they're going to simplify a lot, we'll need that x squared is less than or equal to 2, or x is less than or equal to root 2. And we'll need that, so this becomes rx squared plus, and now lambda 2r plus 1 minus, that's rx all squared should be less than or equal to 2r plus 2. It's essential that Bazza should be able to choose an x less than or equal to root 2 with this property. Let's just multiply all this out a little bit and see if we can simplify. So we get r x squared plus lambda squared 2r plus 1 squared minus, it's not looking super nice, 2 lambda 2r plus 1 r x plus r squared x squared less than or equal to 2r plus 2. It'll be, so where have we got to? Maybe I can make this a bit nicer by letting r get huge. So because Bazza will need this strategy to work for all R. So if R is very, very big, I'm just going to see what happens. I'm going to ignore terms that are not quadratic in R. So what are the terms that are quadratic? So I'm just looking at the main terms in R. So I'll have a 4 lambda squared R squared coming from that 4R squared here. And here I'll have a 4 lambda R squared. There's a 4 lambda, yeah, R squared with an X plus R squared X squared. And that's meant to be less than or equal to 0, so to speak. So because I'm just looking at second order terms. So now I can cancel out the R squared. I've got 4 lambda squared minus 4 lambda X plus X squared less than or equal to 0. So 2 lambda minus X squared is less than or equal to 0. Something's a bit odd here, but I need to be able to, so X is less than or equal to √2. So for that to be, that's going to have to be 0 basically. So we want 2 lambda equals X. So 2 lambda is going to have to be less than or equal to √2. Lambda less than or equal to √2 over 2, which is rather nice. That's what we really wanted it to do. It doesn't feel 100% rigorous, but I think I can make that rigorous, but I'm not sure I totally want to. So let me just sort of say out loud how I believe that this would go. So my belief is that if lambda is bigger than square root 2 over 2, then pick a very, very big R, then this inequality will be violated if it's also violated when we just ignore all the terms that are linear and constant in R. So we just keep the R squared terms here. And if it's violated, that'll tell us that this is as a I lost my thread. What was I trying to say? I was trying to say if lambda is bigger than this, then 2 lambda minus X squared is strictly greater than 0 because X is less than √2, so we can't make it to be 0. So that's strictly greater than 0. That's strictly greater than 0, so that the quadratic in R terms are strictly greater than 0. So when we make R very, very large, this inequality cannot possibly hold because just the quadratic terms will dominate and we'll have a non-zero quadratic coefficient on the left-hand side, a strictly positive one. And so that means that poor old Bazza is unable to defeat the strategy of Alice of just going 0 until a certain point and then jumping to as big a number as possible. So the answer is yes. So we've established that Alice has a winning strategy when lambda is greater than √2 over 2. It's a draw if lambda equals √2 over 2, and Bazza wins if lambda is less than √2 over 2. And I think I've solved the problem, but as always, I now have to look and see whether my hoped for solution agrees with the official solution that's up on the web, which unfortunately is a video solution, but oh, wait a minute. IMO problems and solutions with authors. Oh, but that's perhaps not this year. Oh, yes, it is. Oh, but that just takes me back to the same page. It's a video solution. Okay, let me just try and excuse me there. It's a bit of an advertisement showing, but
It's a broke.
quick skip. Right, now then let's
Everyone, welcome back to
jump to the
by
end.
just forever playing a through k equals to square
I'm
root
just
of
checking I've got the answer
and
right.
wins for
Anyway,
Bazza. Firstly,
I've seen
Bazza
another
has
root 2
no
over 2
Alice.
popping
Of
in
course,
there.
this is
If lambda is greater than
now,
root 2 over 2, then
and we
Alice
can
has a winning
rearrange
strategy.
this
Let's see what happens if Alice
by
keeps playing
extracting
0.
out the
That's
k
looking good.
term.
Sorry, I'll stop that noise. What about if lambda is less than root 2 over 2, then Bazza has a winning strategy, which is indeed the strategy that I identified. And if lambda equals root 2 over 2, it does, the solution does say that it's a draw. So to my great relief, it's always nice. What I've got agrees with the official solution, so I have done that question. And it seems as though I've done it within an hour and a half, so I would be on track if I had actually been doing the IMO. And actually, so I don't attach too much importance to this, but the fact that I've done a lot of chatting would have slowed me down a little bit as well. So I feel reasonably pleased about the outcome of that. Thank you for watching, if you have watched, and I will now finish.